All right.
What days you say the final was?
It's Monday, May the 2nd at 1:30. Yeah. May the 2nd at 1:30. Yeah, it starts 15 minutes earlier than class time. So we're 1:30 to 3:30 is our slot. No. So let's see. Oh, we got 24 of these on the practice test. So I say we do like the first 15 today or something like that, and then 15 or 16, and then we can finish up Wednesday. And then if there's other ones we need to talk about, we'll still have some time on Wednesday to do that. Okay. All right. So probably not going to give you 24. These are just the ones you need to be, the topics, stuff that you need to focus on. Probably will not make it that long. So, and if you didn't hear, I should have the test 4 grades posted by the end of the day tomorrow. And so I'll finish up my second stats class this afternoon, and then y'all be tomorrow. I'll grade y'all. So, all right. Number 1, we're just picking off limits from the graph. Okay. So first one, we got the limit as x approaches 2, and then we got that minus sign up there. Remember what that means? From the left, yeah. So we're approaching 2 from the left. So what we want here, we're approaching the x value of 2 from the left. So that's coming in right there. So what's that limit going to be? 3, yeah, 3. Okay, that's 3. The other one, we've got x approaching 2 with a plus sign, so that's from the right. That's coming in there. So yep, that one's 1. Okay. And it doesn't matter that it's not defined right at 2. Now, that's the whole purpose of the limit, is it doesn't have to be defined at that exact value. We just want to know what it's approaching as it gets close to that value. And then part C, we don't even have to have the graph for. Part C just says the limit is f of x approaches 2. So we got from the left and from the right. So yeah, C is not going to exist because our limit from the left and our limit from the right are not the same. It's been a while since we talked about that, but you have 2 different limits coming from the 2 different sides, and the 2-sided limit does not exist. And then D asks us for f of 2. We just want to know what the y value is when x is 2. Yeah, it's going to be 3. It's going to be 3. It's undefined down here. It's an open circle there. So if we plugged in 2, we would get the closed circle up here, and that's it, 3. So f of 2 is 3. And then we want the limit as x approaches 4. So this one's 2-sided. So we're coming in that way and that way. Our limit's 4. Yeah, limit's 4. And then f part wants the functional value at 4. So if we plug in 4 for x, what's our value out of our function we got? Yeah, we got an open circle, so it's undefined there. So that for that one, we would say does not exist. Does not exist. So that one's just graphically been able to pick out what's going on. I've been able to find those limits and know what they look like graphically. Questions on any piece of that one? you do have questions, don't be shy. Okay. It's okay. It's been a while since we've done some of this stuff. And then plus you've had all this stuff in your other classes you've been having to learn, so it kind of makes it harder to remember some of it. All right, number 2 says use the limit laws to find the limit. We want the limit of this polynomial as x approaches 4. So we've got a limit law for polynomials. We just plug it in, yeah. So our rule, if we have a polynomial, we can just do direct substitution. Okay, so this limit's just going to be whatever we get when we plug in 4. So let's see, I'm going to break out the calculator here. So that's 256, and then minus 32, plus 4 minus 4, so 224. So just direct substitution. You can always do that with polynomials because polynomials are continuous. And a property of continuous functions is that the limit of those continuous functions has to be the same thing we get when we plug the number in for the function. So there's like a lot of sophisticated machinery behind that, but it makes actually finding it easy. We can even say it easy. We just say just plug in 4. There's actually a lot that goes into that. All right, number 3 says evaluate the limit. We try direct substitution. What's our problem? Yeah, I get 0 on the bottom, so we have some ways we can deal with that. Anybody? Yeah, we can try factoring. So that's what I would try here. So the top, let's see, need factors of 2. That'll give us negative 3. So x minus 2, x minus 1. On the bottom, x minus 1. That'll cancel out. So the limit of the thing we started with has got to be the same thing as the limit of x minus 2. So then at that point, we can do direct substitution. And so just do 1 minus 2, so negative 1. So if we have a situation where we get 0 on the bottom, and if you check that one on the top, if you plug in 1, what happens? What do you get on the top if you plug in 1? Get 1 minus 3, negative 2, plus 2, 0. Yeah, so you get 0 over 0. If you're in a situation where you get something non-zero on the top and you get 0 on the bottom, then it's not going to factor. Okay. If you get 0 over 0, then you can try factoring. Okay. Or, at this point, we could even be more sophisticated. Anybody remember what else we could do if we got 0 over 0? Well, we could do what now? Yeah, like you can do L'Hopital's rule, what's that called? Yeah, you can do L'Hopital's rule. Okay. We didn't know about that then, okay, but you could factor or do L'Hopital's rule. Either one would be okay. Okay. We have some L'Hopital's rule problems later, so right here. Okay. All right. I'm going to talk about continuity a little bit here, if it'll load up. Okay. So this one wants us to identify all the x values where we have discontinuities. So remember, function's continuous, where you can, in layman's terms, where you can draw it without picking up your pencil. And then we have discontinuities anywhere. What kind of discontinuities do we have? Cusp is not a discontinuity, but it would be non-differentiable there. That's what you're thinking about there. Got an asymptote or a jump or one more. A hole or a hole. Yeah. So if we're going from the left, where's our first one of those we run into? Yeah, -4. Okay. And then this one's talking about the one-sided continuity. That's not that big of a deal, but so what that's saying is, would it be continuous from the left, or would it be continuous from the right, or neither? This one would be neither, because it's undefined at -4, so we got those three properties of continuity where the limit has to equal the functional value. That can't happen there, so this one would be neither. I'm not as concerned about doing the one-sided continuity, but there we would call that a hole. Okay. Where's our next discontinuity going to be? -2, and what kind would we call that? Jump. Yep. I probably won't make you name them, but they're good to know though. Okay. As far as the one-sided continuity, again, I'm not super interested, but just as why we're here. Okay, this one would be continuous from the left because it's defined coming in that way. And the one-sided limit would be the same as the functional value. It would not be continuous coming from the right because it would be undefined coming from that direction. And so this one's continuous from the left. Okay. Next discontinuity. At 2, yep. At 2, we got another jump. Okay. And on that one, it would be continuous from the right, yeah. The other one it would not be continuous from the left because it would be undefined, so that one's. And then last one, what x value? At 4. What kind would that be? I'm sorry, I didn't hear. Oh yeah, it would be continuous from the right, that's right. What kind of discontinuity would it be? Yeah, we would have an asymptote. And so the asymptote discontinuity is what the text would usually call those is infinite. And yeah, it would be continuous from the right. I circled all of them. I guess we circled them. Not from the left because the limit doesn't even exist on that one if we're going down this way. And it goes forever. So. Okay. No questions on those? Okay. Number 5 says evaluate the limit using the appropriate properties of limits. And key thing on this one, we're approaching infinity. It'd be infinity over infinity. Yeah, it's indeterminate. Yeah, indeterminate. So now we have 2 methods of handling this one. we have so L'Hopital's rule is a possibility because you can use L'Hopital's rule when we have infinity over infinity. Or the other way that we dealt with these, you may remember? Yeah, we can divide everything by the biggest power of x in the denominator. So our biggest power of x in the denominator is x squared. So 8x squared divided by x squared would give us 8. Then we would have 3 over x squared. In the bottom, 7x squared over x squared would give us 7. X over x squared would give us 1 over x. And then minus 3 over x squared. And the nice thing about doing that is that any time we've got the limit as x approaches plus or minus infinity of some number over x, what's that limit? 0. Yeah, that's really x to the n. Okay, so this would be 0, this would be 0, this would be 0. So what's that leave us with? 8 over 7. Okay, so if you do it that method, I need you to show that step where you're dividing, although there is a shortcut. The shortcut is if the exponents are the same on top and bottom, same degree on top and bottom, it's the ratio of the leading coefficient, 8 over 7. Yeah. Or you could do L'Hopital's rule. Okay. So you could do L'Hopital's. Nothing wrong with that. Okay. And then you would take the derivative of the top and bottom. Well, we'll get 16x over 14x. So it would still be an infinity over infinity indeterminate form. So then we would have to take the derivative again. So we would get 16 over 14, which simplifies to 8 over 7. Do it either way. Number 6. Similar. Limit approaching negative infinity. So what way do you want to attack it? And do the biggest power of x again? We got some L'Hopital problems later. The only thing that the infinity being negative affects is sometimes you have to be careful with the signs. But here we're dividing by x squared again, so we'll get 1 over x minus 9 over x squared. And on the bottom, we'll get 1 plus 6 over x squared. So what do we what happens? That's 0, that's 0, that's 0. So we get 0 over 1, which equals 0. 0. Okay, not undefined. You can have 0 in the numerator. That's fine. If you were going to do L'Hopital's rule, which you could, and then we would have the limit of 1 over 2x. and then that's just 1 over an infinity, right? So that would go to 0. Go to 0. So that's the Hopkins rule. Question on that one? Okay. We're into test 2. This differentiate the function. So what kind of differentiation tool do we need on this one? Power rule. Yep, that's all. So 2 times 5/8 would be 10/8. Subtract 1 from the exponent, backward from what we've been doing. If we subtract 1 there, we get x to the 0th, so it just leaves us with -2. And then if we take the derivative of 13, we just get 0 because it's constant. So there's that, and then we can simplify a little bit. Five fourths x minus 2. Not too terrible, hopefully. Number 8. It looks worse, but it's just power rule again. We do need to do a little bit of rewriting. And how can we rewrite that second term? Yeah, 4 times x to the negative 1/3. So 1/3 because of the cube root, and then to move it up to the top, we make it negative 1/3. That's good. Then we can just use the power rule. So the derivative of 9, and the e to the x rule, I guess. So the derivative of 9e to the x is just 9e to the x. The constant just hangs out, and then we've got e to the x is e to the x. And then we multiply negative 1/3 times 4, we get negative 4/3. Subtract 1 from the exponent, so we're subtracting 3 over 3, so we get negative 4/3. And that's fine to leave it like that. Questions on that one anyway? How you feeling so far? So? Not too terrible. I know comprehensive sounds scary, but it's not. In math, it's usually not all that bad. To me, comprehensive Feinland math's not as bad as like comprehensive Feinland history, right? Because then you're gonna remember everybody's name and every date you talked about them. Okay. Number 9 says find an equation of the tangent line. So the first thing we need is the slope of the tangent line. Luckily, the slope of the tangent line is the derivative. Right? That's a formula for the slope of the tangent line. So we can find the derivative here. 3 times 3 will be 9. 3 minus 1 gives us x squared. 2 times negative 1 is negative 2. 2 minus 1 just leaves us with an x. And then the derivative of 3, that's constant, so that's just 0. So then to find the slope of the tangent line at the point 223, what do we do? Plug in the x value, yeah. So this is our x. Yeah. So the derivative gives us a formula for the slope of the tangent line anywhere for any x value where it's defined. And so to find the slope of a specific tangent line, we just plug in the x value. So if we do 9 times 2 squared, this is our slope of our tangent line, minus 2 times 2. So let's see, that's 36 minus 4, so 32. There's the slope of our tangent line. Call it 10. And then to figure out the equation of our tangent line, we can also use the y-coordinate of our point. And we can just fill into point slope form. So we'll do y minus our y-coordinate, which is 23, equals the slope of our tangent line, which is 32, times x minus 2. And this particular answer box wants it to be y equals something, so we need to solve it for y here. So let's see, it'll be y equals 32x minus 64 plus 23. Y equals 32x minus 41. There's our tangent line at the point 223. I would specify. Yeah, we'll probably put it in that form. Slope intercept, like you said. It's not that much more work to get it there, usually. Yep. No. Yeah, I just didn't bring it today, so we just won't use it this week. So. Other questions on 9? Okay. For 10, it says differentiate. What we need to use on this one? Quotient rule. We got a quotient, so quotient rule. And the way I remember it, f prime g minus f g prime over g squared. Or f's the top, g's the bottom. Okay. So let me switch back to red here. This one's not too bad, not too long anyway. So f prime, derivative of the top, what's that going to be? It's 4. And the bottom, 7 minus 6x minus the top, so 9 plus 4x times the derivative of the bottom, negative 6, over the bottom squared. And now it looks like we could probably simplify some. If it was any messier than that, I would just tell you not to simplify. Let's see if it does us any good. So that's negative 54 minus 24x Yeah, it does do some good because minus 24x minus a negative 24x cancels. And then we got 28 plus 54. It's 82. I guess I can finish right in the bottom there. So we end up something not too bad. We end up with 82 over that denominator. Yes, it is. Sorry about that. No need to multiply the denominator out. So. Questions on any part of that one? What are we on? 11? And it says differentiate, find the derivative. How can we approach this one? You do product rule. Initially, something that came to mind is, can I cheat and distribute the e to the x and get out of using the product rule? But then no, we would have to do the product rule twice because we would have 8x squared times e to the x minus 14x times e to the x. So we're doubling our work if we do that. So product rule. The way I keep it in my memory, f prime g plus fg prime. So derivative of our first one, the polynomial factor there. Let's see, we'll have 16x minus 14. And times the second function, which is e to the x, plus the first one, so 8x squared minus 14x times the derivative of e to the x, which is e to the x. And let's see, if we wanted to be fancy there, simplifying, we could factor out e to the x maybe. And then combine like terms. Don't have to. So let's see what we do. It's pretty nice there. If you don't see that, that's not a big deal. I'm happy with the first line as well. Question on that one? Okay. And 12, similar type of problem, but not only does it want the first derivative, also wants the second derivative. Okay. So got product rule. And even if you distribute, you still have product rule involved. So let's see, the derivative of the first term, so that's 3x squared times the second term, e to the x, plus first term, x cubed plus 8, times the derivative of the second term, which is e to the x. And then second derivative is a little bit messier. We've got two product rules we have to do. So I'm looking at this one first. So I'm thinking about 3x squared is the first term and e to the x is the second term. So derivative of 3x squared, 6x, times the second term, e to the x, plus my first term, 3x squared, times the derivative of e to the x, which is e to the x. That's that one done. And now we can think about this one. We've got the second product rule to do here. So derivative of x cubed plus 8, 3x squared, times second term e to the x, and then plus first term x cubed plus 8, times the derivative of e to the x, which is e to the x. And we do have like terms to combine, so we might as well do that. So we've got 3x squared e to the x plus 3x squared e to the x, so that's 6x squared e to the x. Questions on that one, a little messy, but if you just take it one little piece at a time, it's not too terrible. Yep. Yeah, you could. So then we'd have e to the x times 6x plus 6x squared plus x cubed plus 8. You definitely could do that. That kind of makes me want to find the third derivative to see what our pattern is here, because we got that x cubed plus 8 e to the x term that's stuck in both derivatives. To start with, we had 3, and then we had 2 6 coefficient terms. I'm kind of curious about what we'll get the next time, but I won't make you suffer through it. 13. Got 8 e to the x cosine x. Find first and second derivatives. The product rule again. So I'm thinking about it as 8 e to the x times cosine x. So derivative of 8 e to the x is 8 e to the x times cosine x plus, this time I just copy down the first term, which is 8 e to the x, and then we need to do times the derivative of cosine x. What's the derivative of cosine x? Negative sine x. Okay. So you could just do the second derivative without moving the minus sign, but I'm going to move it. Then second derivative. Okay, see you later. Did I lose an E there? Yeah, I accidentally erased that E there. Okay, so we got this repeat situation again. You get that with e to the x. Okay. So the first part, if we're smart, we can kind of shortcut some of this, because the first part we want the derivative of this. Right, AD to the x cosine x. So the derivative of AD to the x cosine x is that. So I'm not going to think about it again. I'm just going to copy that part down. So now we need the derivative of that part. So I'm going to think about it as negative AD to the x times sine x. So the derivative of negative AD to the x is negative 8e to the x times sine x plus, just copy it down so it's negative, so it'll turn into minus AD to the x times the derivative of sine x, the derivative of sine x, cosine x. And that one's kind of interesting. What happens there when we go to clean things up? Yep. And then we got two like terms, so minus 16e to the x sine x. That's our second. Oop. Long, kind of messy, but at least it kind of was a little bit satisfying. It turned out something nice. Okay. 14. Want the derivative. What tool do we need here? Chain rule. Or we could do a lot of product rule if we really wanted to. We could expand it out, times itself 4 times and do product rule, but I don't want to do that. So do chain rule. So it's the derivative of the outside, leave the inside alone, and then times the derivative of the inside. So f prime of x here. Our outside function is the 4th power. So we use the power rule, multiply the 4 out front. Subtract 1 from the exponent. Times the derivative of our inside function, so times the derivative of that polynomial in there. So it's 42x to the 5th plus 24x squared. And just leave it like that this time. Okay. Won't give you anything too crazy with the chain rule because it does get really confusing if you have a bunch of chains and things like that. Questions on that one? No, chain rule kind of one of the tougher ones to pick up the first time through. Okay. 15. What did I say we would do? Through 15 or 16? It didn't really matter. I was just looking to see what I said. And I froze it at 15. Okay. That's a good stopping place. Dean says find the derivative. Got 70 times sine of pi t. Our independent variable here, or variable, is t. So pi is just a number. So we've got 70 times sine of pi t. So we got product rule. And with the sine of pi t, when we take the derivative of that, we'll have chain rule. We've got a combo here. So derivative of 70 is just 7 times sine of pi t plus, copy down the 70, and then we need the derivative of sine of pi t. So we got, what's the outside part on sine of pi t? Yeah, the sine is the outside part, right? So we want the derivative of sine is negative. No, the derivative of sine is cosine. Yeah, now you're good. You're thinking antiderivative. So the derivative of sine is cosine of pi t. But then we got to do times the derivative of pi t, which is pi. That's fine. Let's just leave it like that. Here we're chaining here. Okay. So let's just preview if you haven't looked up. We got a related rates problem, increasing, decreasing, minimum, maximum. Inflection points, concave up, concave down. And we got some L'Hopital's rule, which we kind of already talked about. And we got a few integrals. And then that's it. Okay, so that's what, 2/3 of it covered for today. Okay. And then we'll do the last ones next time, and then have, if you have other questions, have those ready, and we'll talk about those next time too. Yeah. How long do you have for it? It's 2-hour time slot. I probably won't make it a 2-hour test, so yeah, I'll probably make it shorter than that. Just that way you don't have to rush. So. Yeah. Well, I mean, yeah, I guess technically any test can be a 5-minute.